In this section, I'm going to show you how to derive the equations to work out the atmospheric pressure at a given altitude for an isothermal layer. Okay, so we're just going to start off with the hydrostatic pressure formula, which you derived in the last lecture. So pressure is equal to rho GH. Hopefully that's familiar to you. But rather than using height in these calculations, because the height would be the height of the atmosphere that's above us pushing down on whichever plane we're at, it's much better when we want to work out the pressure in the atmosphere to work in terms of altitude, so working from the ground up. So instead of using h, we're going to replace h with minus z. So z is the altitude, and the minus sign tells you that the pressure will decrease as we go further up in the atmosphere, which makes sense. So we're going to work with z instead of h for this, as I say. So we've got pressure is equal to minus rho gz. And we can say that for small changes in the pressure, that's equal to minus rho g delta z, so a small change in z. And if we keep make those changes in pressure smaller and smaller and smaller until they're infinitesimally small, then we end up with this equation. We can write it as dp is equal to minus rho g dz. And so we get to something that we can integrate to work out what it is. And if we were to integrate this, we'd end up with back what we started. But we don't want to do that. We want to do some further substitutions. So first we just rearrange this. So now we've got the change in pressure with dz is equal to minus rho g. So dp dz, so that's the same as saying sort of dx dy in some other sort of differential equations, but instead of change of x is y, we've got the change of pressure with the change in height. Now you'll probably recall that the ideal gas equation explains the relationship between both pressure, volume and temperature. And for an ideal gas, that's defined as PV equals mRT. And notice I've used the form here mRT, so this is the mass and R is the specific gas constant, and for air that's 287 joules per kilogram Kelvin, and not the universal gas constant. Okay, so if you're working in different atmospheres, then obviously you need to put in the R for the gas that your atmosphere is constituted from. So from the previous slide, we had PV equals mRT, and since density's mass over volume, we can rewrite this as pressure is equal to density times RT. And we can rearrange this to make rho the subject, so pressure, so density is equal to pressure divided by specific gas constant times temperature. And if you recall from the previous slides, we had our rate of change of pressure, so our change in pressure with our change in height is equal to minus rho g. And we now have an expression for rho. So from the previous slide, which we determined, so if we substitute that in now, we now end up with the change in pressure with the change in height is equal to minus the pressure times gravity over specific gas constant times temperature. And if we rearrange this now to bring the terms out, so on this side we've got the p's, and this side we've got the z's, although this term will become a constant. We can now integrate this to understand the relationship between pressure and altitude. So if we integrate that, and you can prove this to yourself, so you end up with the natural log of p is equal to minus g z over RT plus a constant, because when you integrate something like that you get a constant. So we need to put in some boundary conditions to work out what these conditions are. And if we put in the known conditions at the base of the isothermal layer, and notice the words here, I've been quite careful in what I've said here. I haven't said ground level, I've said the base of the isothermal layer. So for example, if you're looking at the layers higher up, an isothermal layer up, then you have to come to the base of that layer, not right back down to ground level. So that's what that subscript 0 means. So if you do that, you find out what the constant K is, okay, by plugging those values in. And we can then rearrange that now so that we can end up with our pressure, okay, is equal to the pressure at the base of our layer to the exponential of minus G over RT, where again T is the temperature of the base layer, times our altitude. But we need to be a little bit careful here, because the altitude again itself shouldn't be taken on from sea level. That's not where it has to be. The altitude really should be taken again from the not from sea level. This might not be the best datum, but from the base of the isothermal layer. So if we put that back in, then we now have our final expression where the pressure at a given altitude in an isothermal layer, and as I said isothermal layer, is equal to the pressure at the bottom of the layer times by the exponential minus G specific gas constant divided by the temperature at the bottom of the base layer times by the difference in altitude between where you're interested in and the bottom of the base layer. And then we can use this for our calculations. But before we do, you can show that using exactly similar method to what I've done here, you can show that the density is equal to a very similar relationship and the pressures are substituted out.